Hey guys, my name is Elia Kelso and this is my video presentation for Lab 1, Object in Motion with Constant Velocity. The purpose of this lab is to analyze an object in motion that is maintaining a constant velocity. Then we are using equations in order to try and predict that object's position at a certain period of time, and we compare the results generated from an experimental model versus a computational model. However, in order to understand the purpose of this lab and to conduct it accurately, there is some background knowledge that is needed. First, the relationship between the system and the surroundings. The system is the object in motion, in this case a tennis ball, and is the one experiencing the effects of forces, while the surroundings is the object's environment and typically the one acting on the system. Second, it's important to understand some of Newton's laws of motion. The first law of motion states that an object stays in motion or at rest unless acted upon by external forces. Newton's second law of motion states an object's acceleration is dependent on two things: mass and the net force acting upon the object. However, in order to have a constant velocity like we do in this case, there can be no net force because there can be no acceleration. Also on the slide, I included a graph just illustrating what constant velocity looks like on a graph, and this came from my glow skips. On this slide, I included crucial equations that were used in this lab, not only on Tracker, but also for GlowScript. The velocity and position equation are both heavily based in Newton's second law of motion. These were both used to predict the motion of our object in the lab. As you can see, they help find final velocity and final position. For the velocity equation, the components include initial velocity, net force, mass, and delta t. For the position equation, it utilizes initial position, average velocity, and delta t. On this slide, I also included the average velocity equation. It's important to note that the assumptions made for this lab is that friction and air resistance have no impact, which is what allowed us to have a net force of 0 on the object. This video represents how I got my data for the experimental model. There were 0.033 seconds between each time frame, and I used the center of mass of the tennis ball to mark the position of the tennis ball at every new time frame, which is what gave me my data points for the experimental model. This is the code I used for GlowScript in order to obtain my data for the computational model. As you can see in the first picture of the code for the initial position, I tamed that number from Tracker, and the ball's velocity was found utilizing the average velocity equation, which I attached my work right beside that picture of the code. Then obviously I set the net force to 0. This can be found in the bottom picture of the code. It included the equations I mentioned earlier for predicting velocity and position in the future. On this slide, I included my graph titled Experimental Model versus Computational Model. The x-axis is time in seconds and the y-axis is position in meters. By looking at the graph, you can see that the experimental and computational models started off similar, but really started to diverge as more time passed and as the graph moved further along the x-axis. For this lab, we were only focused on motion that occurred on the x-axis, specifically the positive x-axis, because my object moved from the origin to the right. We can see that the computational model is perfectly linear, while the experimental model exhibits inconsistencies. The computational model shows an object with a constant velocity, while the other experimental model does not, indicating that the net force is not 0 and some other force is acting on it. If I was to switch my object to moving along the negative x-axis instead of the positive x-axis, it would cause my graph to slope downward instead of upward. And for the second question, no, it is not possible to say how many pushes and pulls are added together to give a 0 net force. It is important to note that there very rarely in the real world is ever a 0 net force because typically there is some sort of force acting on an object. There's definitely a lot of human error possibility in this lab. For instance, I had a hard time rolling my ball or getting my ball to stay in a straight line due to the surface of the table I was rolling it on. And of course, if an object changes direction, it means there is a change in velocity. So that is one possibility of human error. I just want to thank you guys for watching.